So obviously the answer is quantum computing. Many years back, there is the Professor Paul Device, who is the theoretical physicist, and he is the professor in Europe, and he said the 19th century was known as the machine age. So basically, in that 19th century, there was the major development of the mechanics, classical mechanics, and the other things. Then the 20th century will go down in the history of the information age, and definitely we are facing all these things, like how that internet or information technology is developed, and are they have the thrust areas in today's domain. So I believe the 21st century will be the quantum age. So he has already connected the things. Machine age, the ancient thing, or we have to say this is the past, but very important. Again, we move from machine age to the information age, and definitely now we will move from information age to the quantum age. And definitely the examples of quantum age will be the quantum computing, quantum theory, and there are so many things in that particular domain. For example, you all already know about this particular device. This was the computer processor in the early days, and we have moved as there is the progress in the technology. We have moved from the big machines to the small chips. Now, from small chips, we will move towards the atoms. Why all these things are going on there? Because technology is very important part. Technology is making devices smaller and smaller and smaller. So it is very important and very fundamental thing. Everybody knows, but we have to realize the things, that is Moore's law, and that Moore's law is applicable in electronics, in computer science, in other areas also. So for example, we are reaching a point where classical physics is no longer a suitable model. Meaning is very simple, that the physics which supports the classical laws will be no longer suitable. And why? Because this will be classical physics is not applicable at the size of atom, because hardly we have to understand that the sizes of the chip is of the order of micrometer, right? Micrometer or millimeter, but within that millimeter the devices over there will be of the order of micrometer, and now it is decreasing according to the Moore's law. It is decreasing and decreasing and decreasing. So nowadays we have to say, for example, there is a bit or qubit that is made up by suppose 6 or 8 atoms. For that same means when we will move, or we have to work for the atomic level, where the size is of the order of nanometer, the concepts of quantum physics or concepts of quantum laws will be very important. And I think it is one of the most fundamental thing in terms of the physics, that wherever with the size and light, means matter light interaction, the matter and light wavelength should be of the order of same. Otherwise, that will be not applicable. There will be no interaction. Hence, if I have to interact the light with matter, for same, the wavelength of light should be of the order of matter. So, for example, like 8 angstrom, 10 angstrom, or 100 angstrom magnet. So basically, Moore's law examples are very simple. For example, size of transistor was 5 nanometer in 2019, and in 2020 this was the 3 nanometer, and that is just because of the technological development. Now I am moving. For example, this was the slide which support our answer why information age is going towards the quantum age. Now, what about in this slide? In this slide, I want to mention that if I have to explain the non-classical light, we need to start from the optics first. So within this slide, I am explaining you the classification of optics. Optics can be classified in three categories. For example, classical optics, which we have already heard in our school days. For example, light is always a wave, atoms are dipoles, and wave optics covers all geometrical optics. So basically, this classical optics is a part where we can feel like laws of refraction, diffraction, and so on. At the same time, there is another word which is called semi-classical optics. And what is the meaning of semi-classical? Means light is still a wave, but the matter, size, or whatever is the materialistic things, they are quantized. So जहाँ पर हमने means whenever we have considered it that atoms are quantized but light is a wave, that will come under the semi-classical optics. Now where we lie means my non-classical state, or as I am explaining the non-classical lights, where that lie in the heart of the quantum optics. So that is the third category. And in quantum optics, light is photon now. Light is not a wave, light is photon. Obviously, light have dual nature, but for observing these quantum optics effect, we need to understand that light will behave as the photon. And if I have to explain the photon, that is just the energy packet and so on. But overall, this is the journey from wave to photon. And what about the atoms? Atoms are quantized. So it means both are quantized basically. Both are having some orders, both are having some integral multiples and so on. So basically, my topic of non-classical light comes under the domain of the quantum optics. Here I want to start the things related to the early history. If when this all these things starts, because as in my last slide I am talking about the light as the photon, and light as the photon was not discovered in 1600 or 1700 or 1800. It was first described in obviously the 1900. So in 1901, this was the scientist Planck, very famous scientist Planck constant, we already know everybody. He has given the theory of black body radiation, and that theory was explained with the help of the Planck's law. So basically, origin of photon, origin of this thing was 1901. Second, later Einstein have explained about the photoelectric effect and the other effects, basically, which are direct related to the quantum optics or quantum information directly or indirectly. So I will point to some important points, like there is the intensity interferometer, and their development was in 1956. So this is famous HBT experiment in which a light will pass through the beam splitter, and after that beam splitter, if we are considering it as wave, that will be 50-50%, but if we are considering it as the photon, so then there will be the certain probability of getting photon on either side. So that is very important point, and I will explain this particular HBT system in my further slide. What about in 1963? This was the year. This was the year which was very important for the development of this term, or for the coining of this name, like non-classical light. So it was Glover and Sudarshan. So basically, Glover independently, Sudarshan independently, but both have coined this name non-classical light in 1963. So I will definitely explain what is non-classical light. But as per the development, this term was coined in 1963. Thereafter, after this development, means for example, after 1963, There are many developments related to the quantum information or quantum optics. For example, Kimball and Mendel has given the photon anti-bunching, and frankly speaking, photon anti-bunching cannot exist in this classical physics. In classical physics, we cannot explain photon anti-bunching. That can only be explained with the help of the quantum laws. Similarly, you already have heard about the Bell inequality. Definitely, so many have learned persons already explained about the so many points related to the quantum information. The third coin is 85. In 1985, this was the term squeezed light, and I think many of the fraternity already know about the squeezed light. Why it is so much important? Squeezed light is again the example of non-classical light. Photon anti-bunching is again the example of non-classical light. And squeezed light was heard in the famous gravitational wave detection. And with the help of that gravitational wave detection, we can observe so many number of things. We can explain so many number of phenomena, because the in planetary system, there is a big role of the gravitational waves, and this was the state of that light which was useful to detect the gravitational waves over Earth. Then there is the single photon interference experiment, quantum cryptography, again very important, because in this internet age, cryptographic, and that should be supported by the quantum mechanics. And I think for this particular topic, our mentor, our head, Professor Pathak, will give a talk after 1 or 2 days. Then in 1997, there is the term coined quantum teleportation. Again, teleportation is very important. Why? Because of the quantum communication. So these are the major developments in these years. And what are the emerging quantum technologies based on non-classical nature of light? So I will cover 2 to 3 more slides for these emerging quantum technologies. Then I will explain properly what is non-classical light and how that is useful, and how can we do research in that particular area. For example, quantum key distribution, again the part of the quantum cryptography. And in quantum key distribution or quantum cryptography, we can understand there will be the two parties. There will be the two parts. One transmitter end, the another one will be the receiver end. So I have to say there will be one end like Alice, another end will be Bob, and in between these two, the communication will take place with the help of the qubits instead of bit, because as we already know that within the channel or within the communication, the information will be transferred from one place to the another place. So for that information, what is the light? Because this is the optical communication. So for optical communication, if we use the classical light within the fiber, so definitely that will be the classical communication. But if we use the quantum mechanical based light like qubits, so then definitely there will be the quantum cryptography. Also, we have to say quantum key distribution, because the key generated at one end will be the key generated at one end will be traveled from long distance from Alice to Bob, and that key will be supported by the qubits. And within this qubits, we are writing over here like A0, B1. So basically, this is the superposition of state where A and B can have any value from 0 to 1. If A is 0, so only one state is there. If B is 0, so only A state is there. But in electronic bit, the A is 0, so then B will be there, and B is 0, so A will be there. So that is called means 0 and 1 state is defined as the electronic bit. But in qubit case, the A and B both are non-zero, suppose. So it means A can be or cannot be. For example, A can be 0, B can 1, B can be 0, A can 1, as well as there is the third possibility, which justify the existence of qubit. For example, A can be 1 by root 2, B can be 1 by root 2, and their independent probability will be 50-50%. And that 50-50% example is just a simple beam splitter. A single photon is suppose passing through the beam splitter that have possibilities on both ways, and in both ways the probability will be 50 and 50. Obviously, this particular topic will be better explained by Professor Patak. Today, in my today talk, I want to cover the non-classical nature of light. So basically, qubits are non-classical, are the non-classical state of light. Non-classical state of light, superposition states, and qubit. Satellite QKD, 1500 kilometer distance. This is reported in the China report. Quantum cryptography, quantum communication, and definitely it is very hot topic, very important topic, and it is good. It will be covered in this particular summer school. It will be highly helpful, and Professor Patak is well-known expert for this. Emerging quantum technology based on non-classical nature of light. For example, these are the companies: D-Wave, IBM, Intel, Google, so on. So all these companies are producing as well as investing too much money in this particular field. And why too much money? As I have already explained you, according to Moore's law, according to quantum age, all these concepts will be transferred towards the quantum technology, and all these things will be supported by the quantum laws. So basically, D-Wave company, Canadian company, have given their first multi-qubit processor. IBM also provided the quantum computing processor. So this is the D-Wave company processor, in which there will be the processor chip and there will be a multi-stages. And obviously, the concept are also covers the field of superconductivity. So it means these are the processors which having the qubit system on the basis of the superconducting laws. There are so many videos available over the YouTube. You can just search D-Wave quantum computing, D-Wave quantum processor, and you will have it will be fun, right? So quantum computing again, D-Wave. This is just like a big box, big room, big box, big room, and within this big box, big room, this is the position of this processor chip. And there, these are the multi-stages, and these multi-stages are definitely supported by some quantum computing system, and so on. Programmable quantum chips. So basically, photonics field is also supported by the non-classical nature of light, because there will be the qubit-based chips, photon or qubit-based chips. Quantum enhanced metrology. This is again a very hot field in which there is so many work related to that. And LIGO, advanced LIGO upgrade. So basically, as I have already mentioned you, they use the squeezed state of light. So basically, squeezed state of light is the non-classical light, and that is useful in this particular domain also for the gravitational wave operation. And definitely many more. So there are so many number of fields, so many number of applications where the quantum laws or technology is supported by the quantum laws. For example, quantum dialogues, quantum cryptography, tense coding, quantum interferometer. Obviously, we can understand the MZ word over here. That is basically the Mach-Zehnder interferometer. And Mach-Zehnder interferometer is very important in experimental quantum information, quantum teleportation, quantum games, quantum empires, and so on. So there are so many number of things where you can do work but at least within this talk, I wanted to explain, or I want to explain, the non-classical light, and all these phenomena are directly related to the non-classical state of light as the source, because for all these things you will require a source, and the obvious preference will be the non-classical light of state. And as I have already mentioned you, anti-bunching, squeezing, subposition in photon statistics, entanglement, all these are the examples of non-classical state. There is the slide quantum dialogues and entanglement based, because entanglement is a quantum phenomenon, and entanglement based protocol for two people, because for dialogue you require the two people at least. So entanglement based protocol for two people to simultaneously exchange their messages. So basically, I think it is more than sufficient to understand what will be the meaning of quantum dialogues. For dialogue, you require two parties, and within these two parties, you want to exchange some information, you want to exchange some message that must be supported by the entanglement-based systems, entanglement-based protocols. So if the protocol, the algorithm is based on the entanglement, so definitely that can be the domain of the quantum dialogue and so on. Next part can be the quantum teleportation. Again, very, very important. In teleportation, there will be the input state, and we can have the state over the output end. So basically, there is a circuit. Quantum teleportation is again the field of, as I have told you, quantum teleportation is again the field of quantum information processing. And the important part is the qubits applicable for this particular circuit will be the quantum mechanical principle test. And here we can understand there are the four Bell states. You must heard about the Bell states, and with the help of these four Bell states, we can have the transportation of qubits from one end to the another end. Again, there is the Heisenberg gate, C0 gate. Obviously, there will be a quantum circuit, and that circuit, or we have to apply the qubits over the circuit, and at the output end, we can understand the quantum teleportation. And one of the most important part of the quantum teleportation is the original information will be transferred at the output end, just like the fax machine. If we put a paper in the fax machine, there a copy will be generated at the output end. But it is very interesting, it is very, very important in the quantum teleportation part that in this case, the original source will be transferred at the output end. Definitely that is a copy, but as this is supported by the quantum laws, that will be as it is if there is the absence of any quantum noise. Obviously, whatever will be the noise part, that should be reduced, and makes it, their original form should be transferred. And at the input end, the original power form will be destroyed, because as per the quantum mechanical laws, no cloning form, copying is not allowed. And this is one of the most fundamental aspect of the quantum technological qubits, that as they cannot be copied, so therefore it is highly secure. And as because quantum mechanics, you already know that in quantum computing, the system, the processor is very, very fast, supported by the 2 to the power n. So therefore, it is duty of the research generation that to protect the system, to protect the hacking of the things, we need the quantum technology. So basically in this quantum teleportation, I am not going in much detail of this circuit. I just wanted to show here that quantum teleportation having the source as the qubit, and definitely these qubits are entangled, and that entanglement is again the example of the non-classical state. Again, obviously, this is the quantum communication, quantum cryptography. Within this picture, we can understand that there is the source which have the optically polarized photons or optically polarized qubits. So basically, photon polarization is very, very important. If we are talking about the quantum information theory, if we are talking about the information theory, we are not much concerned about the polarization, but at least for the quantum information theory, polarization is very, very important. And that polarization means instead of 0 and 1 state, we have to understand their polarization and superposition. So for example, within this particular picture, this is the input end, there is the output end. There is a channel in which photons are having the different polarization and having some states like 1, 1, 0, 0, 0, 0. Photon sequence can be like this. Base sequence can be like this. Basis means basically the things are supported because we have to give the information, and here there is the possibilities of 0, 1 as well as the plus minus or plus cross. So basically now there is the freedom of 4, and that plus cross is developed because of the polarization of the light, compatibility, and finally there will be the key. So there will be the testing part and other part. Again, it will be covered in the quantum cryptography. So for this particular thing, or the idea of this was first introduced by the Arnett and Russell. Basically, you are already have heard about the BB84 or B92 protocols. Again, as I have already told you, there are so many number of things like quantum information theory, dialogue, cryptography, Mach gender, teleportation, vampires, and so on. Now, let me come to the my part, where this non-classical state lies. So, over the screen, you can see there is the what are the examples. The examples of classical light are like ordinary lamp, ordinary bulb in our day-to-day life. I have a torch, not LED based, suppose, but whatever be the bulb, tube, normal light, all these are the thermal sources. And this is also called the punched light. Punched means the light having photons, and photons are coming in bunch. They cannot be separated out, suppose. Or I have to say within a pulse, there are 1,000 photons. So that kind of situation, or I have to say in a very simple manner, the examples of classical light, we have to understand that there are the tube lights, bulb, or all our day-to-day light sources are classical light. Then there is the second source, which is the laser light. And laser light is definitely different than that. Is just am I audible?
Yes, sir.
Okay, thank you. So the second category, laser light. And laser light have a coin term coherence. I will not go in much detail of that, but if I need to understand how this laser light is different than the classical light, this is highly coherent, this is highly intense, this is less diverging, and it was again one of the very important discovery in 1960s, where laser was discovered by the Mammon. And important part was he laid as laser is also my specialization, that's why. But laser has highly intense source, and for experiment point of view, we require some time, or I have to say for laser field interaction, for laser matter interaction, the laser light was very, very useful. And we have already observed so many number of developments related to the optical domains. The third part now, where this non-classical light lies, because all or non day-to-day light sources are non-thermal sources. laser light is coherent. These are no incoherent. So basically, laser light is different than that. But if I have to say what is the connection in between these two, here all the photons were oriented in other direction, means that is incoherent source. They have no phase matching. But in case of coherency, they are matched. It means for they were going in different direction, they were having different phase. In laser light, they all have the same phase. So that is the important part of the coherence. Because of this coherence, we have the laser source, and obviously man-made. So now point is that if we can pass our journey from the normal sources to the laser light, can we go beyond that? Means beyond that, what is the meaning of that? If can we go beyond that, and can we get the single photon on demand? So obviously, so there is a world, there is a big world of a non-classical world where the light can have form anti-bunched light. And anti-bunched light is a light source where the photons are coming from the source in independent manner, or in one to one, or in single to single. For example, like single photon source, I have to just I have to imagine I have a laser light which is the continuous source. So light waves are coming. But in case of the single photon source, I have to just visualize. I have a torch and only single photon is coming on demand. So obviously that is a big challenge for us. But single photon sources are very important in the domain of quantum information theory, in the domain of quantum communication, and because of that, and obviously the single photon can only be achieved with the help of the non-classical phenomena of lights. And the meaning, okay, suppose I have to say what about the definition. The non-classical light are not supported by the classical laws of physics. They cannot be explained with the help of the classical laws of physics. They don't have any existence in with the help of the classical laws of physics. Single photon source, anti-bunch light, entangled photon pairs, they don't have any classical existence. They have quantum existence, and that's why we are talking about they are non-classical. So this is basically the point. This is basically the part where we have to understand that how we can categorize the non-classical light from the normal day-to-day light or normal classical communication. And obviously, the overall communication system is supported by the non-classical lights. Then squeeze light, LIGO, you already have heard about the LIGO setup, Laser Interferometer Gravitational Wave Observatory. This is one of the biggest achievement by the scientists, as with the help of a big interferometer system, which is based on the squeeze light, they can easily measure the gravitational waves which are coming from the terrestrial bodies. And once they can achieve, or once they can detect the gravitational waves coming out from those sources, so they can have so much data related to that, and they can study the things. So this is a major use of the non-classical light. There are again two terms now. Earlier we were already aware with E bits, it means normal classical communication. Now there is the next term is qubit. So for qubits means quantum bits. So bits means 0 and 1, but it is quantum mechanical in nature. Now there is the third term, that is qubits, not qubits but qubits, means there is the d-dimensional state. सिर्फ 2-dimensional state नहीं है, d-dimensional है. So basically the quantum Q stands for quantum and D stands for the d-dimensional state. But है फिर भी. So in this particular picture, I wanted to show you that there is the cavity system in which we can claim a single photon. Obviously, it will be supported by the nanotechnology too. So, if I am talking about the nanotechnology, nanotechnology is again very important part, and in a very simple manner, I have to say we are reducing the size of the matter from micro to nano, and we want to achieve as minimum as possible. If that is one dimensionally confined, that can be two dimensional confined, that can be three dimensional confined. So for single photon generation with the help of the nanotechnology, we will prepare the quantum dots, and those quantum dots must have as minimum as possible number of photons, as well as the as minimum as possible number of atoms. Entangled pair photons, for example, I have a laser pump. There is a polarization based beam splitter, and with the help of that, we can split the light, right? So we can split the light, and we can split the light. So basically, for example, if there is the half, so then, and I think there are two parts, so there will be 50 and 50. So if this 50 and 50, we usually think in terms of the intensity, but I have to understand in terms of the counts, in terms of the numbers. If there are the 100, so obviously there is the 50 photon will go in this direction, 50 photon will go in this direction. And now just imagine if we have the another single glass slide, I have put over here, and there are 50, they can be reduced to the 25. Similarly, we can have the 25 to 10, 10 to 5, and so on. So it means we can have the single photon source as well as the entangled photon pair. So single photon source, we particular trick say we can achieve, right, with the help of the glass plates. But what about the entangled photon? उनको entangle कैसे करोगे? So that is again an important point. So for example, laser light, edge passes through the non-linear crystals supported by the PVC. And once that it passes through the non-linear crystals, then at the output end, we can have a light in which there will be the two photons which are entangled pair. So let me go for the next part. Squeezed light. Within this particular picture, we can understand the squeezed light, and obviously mathematically also I will explain it in the later slides. But at least within this picture, I have to say, if there was a complete circle, if there was a perfect circle, so then that circle, if we reduce that circle in a particular, obviously that circle will have x and y, and if we, and that x and y can be their amplitudes along those directions. So if we reduce their amplitudes, if we reduce their uncertainty, if we reduce their variance in a particular direction, so यहाँ पे वो भी होता है. For example, I have to say the Heisenberg uncertainty principle. I don't want to go in much detail of that, but as per the Heisenberg uncertainty principle, there are two parts: one uncertainty in position, another uncertainty in momentum. Similarly, in terms of the field, there can be delta E, delta B also. So with the help of the uncertainty principle, we can achieve the squeeze light also. I will explain in later slides again. Parallel processing in 2D 01 means basically parallel processing. Yes, parallel itself is a very important term which distinguishes the E bits and Q bits. Similarly, parallel processing in many dimensions means parallel processing in only two dimensions. For example, 0 and 1. As we already know that about the qubits, the parallel processing, because if I am talking about the E bit, so there will be a processor which will work either on 0 or either on 1. But in quantum mechanical systems, there is parallel processing possible for the two dimensional state like 0, 1 at the same time. It means that can be 0, that can be 1, and that in between means superposition, means non-classical. Similarly, in case of qubits, there are parallel processing in many dimensions. So now you can understand the part how obviously the qubits are the next to the qubits. Obviously, qubits the real future of quantum computing. If we are working in the domain of qubits, so definitely qubits are the real future. And qubits can have 10 or more quantum state. Qubits can have 10 or more quantum states simultaneously compared to just 2-4 qubits by Charles Figure. There is a reference, you can go through with that. You can read about the qubits and their uses. Definitely within a system, within a circuit, if I have to say, I have a chip over which I can see the input and programmable filter, phase modulator, programmable filter, single photon counting system, entangled photon pair, and obviously this is a world. This is a world where the huge of non-classical light. ABCD means how we can explain the non-classical states of light. A state which can be understood only by a quantum mechanical description. So language or definition is very, very simple. The state of what? The state of light. The state can also be for a matter too. ऐसा नहीं है कि in matters non-classical states are not possible. Obviously, in case of matter too. But here I am talking about the light. So then a optical state, a state of light which can be understood only by a quantum mechanical description is called a non-classical state. And non-classical states do not have any classical analog. Commonly, standard deviation, which is also called as the, which is also related to the variance, or I have to say for the communication part, noise. Commonly, second, standard deviation of an observable is considered to be the most natural measure of quantum fluctuation associated with an observable. For example, I am measuring the electric field, so definitely there will be a delta E part will be associated with the E. Reduction of quantum fluctuations means I am getting a system and there is a permissible limit of delta E as per the classical laws. And if I reduce that noise below the classical laws, means with the help of the quantum mechanical laws, the coherent state level corresponding to a non-classical state. So next, an electromagnetic field is said to be an electrically squeezed if uncertainties in the quadrature phase observable x, because there is the quadrature phase observable like x or y. If an electromagnetic field is said to be electrically squeezed field if uncertainties in the quadrature phase x reduces below the coherent state level. Okay, below the coherent state level means, for example, coherent state level is half. So half and half. And if I have reduced that particular part below half, so on the obviously on the cost of the other part, so then this will be the, this will call the squeezed field. So as I was talking you, the conversion of a circle to the ellipse, and definitely there will be major and minor axis. So that minor axis part can be utilized as the squeezed light. Similarly, how can we understand the anti-bunching? Squeezed light is directly related to the electric field quadratures and noise part. But anti-bunching is directly related to the number of photons, means defined as a phenomena in which the fluctuations in photon number reduces below the Poisson level. And what is the meaning of that? Hence, कहता है कि anti bunching is defined as, anti bunching physically means in the visualization, I have to say anti bunching is just simply there is a source which is producing 5 photons at a time. But there is another source which is producing 5 photons in different time, means one by one, or 2 photons at a time. So basically, the journey from multi-photon to single photon can be achieved with the help of the anti-bunching, and it can be defined in terms of the photon numbers. Because for any source, there can be a counts of the photon. Obviously, we can measure the intensity, but with the help of that intensity, we can understand, we can calculate the counts too. So basically, this depends on the numbers n. And what about the Poisson level? Poisson level is basically correspond to the laser light. क्योंकि जैसा कि मैंने आपको अपनी पुरानी स्लाइड्स में बताया, this is a journey from classical sources to laser, and definitely laser to another, means laser to beyond world where quantum laws is only applicable. So Poisson level is corresponding to the laser light, and if for laser light the mean n, means mean number within the pulse, and here delta n square, where delta represents the variance in that particular count. For example, here this is variance in electric field, that is E delta I. Similarly, this is delta n. And if this, in case of laser light, it is equivalent. In case of classical light, it is greater. But in case of non-classical or anti-bunch light, it is lesser. यानी कि हम उससे भी ज्यादा रिड्यूस कर रहे हैं, उसके जो भी वेरिएशन है, whatever be the standard deviation, that is going to reduce lesser than mean. So if as per the mathematical definition, delta n square should be lesser than the n, and if that particular kind of light obeys this law, so light will be defined as the anti-bunch. What we expect with anti-bunch light? Obviously, so this is a visualization simple. Like I have a thermal light, ordinary lamp, so there will be a random emission of the within that particular random emission. It is possible there are 3, sometimes 2, there is 1, and with the help of their counts as well as their position, we can understand the mean and variance. Similarly, in case of coherence light, their mean and variance can be calculated. But what about, and coherence light means laser light? As I have already told you, this is a journey from ordinary to laser, and laser to the non-classical world of light. Like anti-bunch light, they are more spacious, mean and variance, very less variance, mean than mean. So in this case, that mean and variance can be equal, mean and variance, variance is greater, and here variance is less. So this is the non-classical. For making single photon source, the light must be non-classical and anti-bunch in nature. And how can we do work with that? Obviously, the light or electromagnetic field can have their quantum state, and for those quantum state, we can apply so many number of laws and experimentally we can work. This is another picture in which the thermal light, laser, and non-classical. Basically, these were the 3 categories. Thermal means classical, laser, obviously this is a boundary of non-classical world and classical world. Thermal light incoherent होती हैं, laser are coherent light, non-classical lights are anti-bunch, squeeze, Poissonian, and so on. So this was the famous HBT experiment in which the light was considered as the photon, and if these photons are passing through the beam splitter, that have certain chances, certain probability to go in this direction or this direction. So point is, if there is the photon nature of light, suppose I am assuming only single photon, so either this will click or this will click. Obviously, initially there is the probability, but after measurement, that is fine. Similarly, if there is the multi-photons, the photon will go in D1 or D2. And with the help of this correlation, with the help of counter, with the help of timer, we can understand that particular. The meaning of non-classicality as mathematical criteria, because for research we required the criteria, mathematics behind that. We have to check that for the existing states, and on the basis of results we can predict, yes, it will be a useful source or not, it will be anti-bunch source or not, it will squeezing it possible or not. So definitely there are mathematical criteria related to that. So reduction of quantum fluctuation in terms of number, in terms of phase, in terms of field below the coherent state level corresponds to a non-classical state. So this is a perfect definition now. There can be other definitions too, but at least in terms of the anti-bunching, squeezing, and other phenomena, this is one of the most suitable definition where this reduction, this variance is for a particular quantum state of light is lesser than the laser light. And laser light have Poissonian statistics. If I am talking about the photon distribution within the laser light, so that is a Poissonian statistics. And if any state which is observed, any state, for example, in a particular lab, we have generated a particular state, and I want to check whether it will be classical or non-classical. So this is one of the beautiful, one of the standard, or one of the important criteria to justify our answer. Second thing, again, all these major things, all these important discoveries have their roots in basic principles, and obviously this is supported by the Heisenberg uncertainty, which was discovered quite early in 1920s or at that particular time, because there was so much development from 1900 to 1940. Now, a natural question is, as we already know that there is the mean, there is the standard variation, there is variance, there is the kurtosis also. Means if there can be delta A cube, there can be delta A4, there can be delta A5, where this A is either number or field, as per my work. If A is either number or field, but I am interested for this power, I am interested for this order. If this is more than 2, then there is a development of the higher order non-classical. So interestingly, sources are non-classical, and within that non-classical, they can have their higher order too. Similarly, higher order non-classicality is described by nth order movement, because it is also called the movement. So nth order, this is second order, there can be third order, there can be fourth order, there can be fifth order. And again, the question is, how will we work? So for same, again, I will explain you some mathematical criteria, but as per the understanding, this is the basic fundamental of this field, where A operator can be written in terms of annihilation and creation operators. I hope you have already heard. If you have done some work in the basics of quantum optics or quantum information, or definitely the quantum mechanics, you must heard about the annihilation and creation operators, which are very useful for doing such mathematical things under framework of second quantization. Again, definitely there will be a natural question. Okay, what about sir first quantization then? So for first quantization, I have to say the things related to the, means the Bohr have given the electrons are distributed in well-defined energy levels within the atom, comes under the quantization. But later, the light is also, light waves is quantized, so definitely that photons or their distribution can have further quantization too. They can go up state, they can go down state, and definitely that world also the quantization. So basically, quantization for optical field, quantization of light will be related to the second quantization, and the first will be related to the material, as per the best of my knowledge. Now, these are our publication within this field related to the non-classical states and higher order non-classical states. I will explain you some of our results, some of our mathematics, which can be easily understand. Why higher order? Obviously, the next question is why higher order? Higher order non-classical criteria are more powerful in detecting weak non-classicalities. Means within this word, experimentally, I want to measure a light. Light itself has very low intensity, as well as the nature or amount of non-classicality is very, very weak over there, which cannot be detected with the help of the second order. So we require third order, fourth order, fifth order, seventh order. So it is quite possible that is non-classical for the seventh order, but that is not non-classical for the third order. So that's why this is the definition. Higher order non-classicality criteria are more powerful. इससे normal criteria से lower order non-classicality criteria in detecting weak non-classicality. Recently, it is experimentally verified by some scientists and reference it over here. So that's why our work is motivated for the higher order non-classicality. So now what are our challenges? We can do a work for the higher order non-classicalities like higher order staging, anti-bunching, higher order superposition photon statistics, higher order entanglement, Wigner function, Wigner volume, and so on. List is quite long, but every calculation related to the any particular phenomena for variable number of states can provide you the paper, and we have the paper in that particular paper. This is our recent publication. These are some of our recent publications related to that. So right. So within this particular slide, means all these phenomena have mathematical criteria, but I will not explain everyone because within this school there are the students, there are the faculty, there are the fraternity, which have different research areas. So I will just explain in support of my topic higher order non-classicality. I will just explain the single criteria which can be explained mathematically. For example, this is the criteria of HOA, higher order anti-bunching. A dagger is the annihilation operator, A is the annihilation operator, and when I am talking about the L plus 1, L plus 2, L plus 1 means if L is equal to 1, so then there will be the A dagger square, A square. Here there will be A dagger A and whole square. तो दोनों टर्म में बड़ा टेक्निकली डिफरेंस है कि यहाँ पर I have to take the average of A square, A cube, A4, A4 means first of all we are taking about the consideration of annihilation and creator operator for their powers and then taking the average. And here first we are taking the average and just doing the power. तो इसको यदि मैं दूसरे टर्म्स में सोचता हूँ तो I have to say if I have a to the power 5, a to the power 5 उसको एवरेज ले रहे हैं तो it means itself a2, a2, a3, a3, a4, a4, a5, a5. There can be so many number of possibilities which should be measured in the lab. And winning is what for that? A dagger A is just the quantum average. It means it provides us the mean value. And what about these? These are the movements. And what is the meaning of that moment? This will show you the probability of, suppose if L is 1, so then there is power 2, there is power 2, there is power 2. So A dagger A square is the probability of getting 2 photons at a time. If there is the A dagger A cube, there is the probability of getting 3 photons at a time. A dagger A power 4 will provide you the probability of getting 4 photons at a time. But what about here? If power is increasing, means there is A2, A2, so then this will provide you the probability of getting them simultaneously or separately. And if this is less than this, so definitely we can have the criteria fulfilled. So if this criteria fulfilled for same, this should be lesser than 0. This should be lesser than 0. So is the quantum average of the number of operator and the ladder operators overall, this is a criteria which is provided with the, and these calculation can be done with the help of any state. For any state we can apply them, we can get the results, we can verify them, and once our results are matching, definitely we will get the criteria satisfied. So D is lesser than, correspond to higher order anti-bunching, D is equal to 0 corresponding to higher order coherence, D is greater than 0 correspond to the super bunching, higher order bunching, manifold bunching. Similarly, other criteria of non-classicality, because world is very big, zoo hai. We have to say there is a zoo of non-classical phenomena. The paper clip, this is a picture, this is a screenshot of one of the paper references over here. Testing non-classicality in multimode. A unified derivation of classical inequalities. So basically these are the criteria. These are the name. Non-classical effects, quadrature squeezing, principal squeezing, sum squeezing, multimode, difference squeezing, subposition in photon number, Queche-Schwarz inequality, Muir-Head inequality, and so on. And all these photon anti-bunching, all these are the criteria. There can be their orders, there can be their simplification, there can be, in my earlier slide, I have mentioned that capital D. Here there is a notation of small d. But all these are directly or indirectly related to the creation or annihilation operator. And with the help of that, all these must satisfy. And once that is satisfied, to that particular phenomena is possible in that particular state. At least for my work, there are the criteria, like for anti-bunching, this was the criteria. For Hillary squeezing, Hillary is basically the name of the scientist. So basically squeezing is of again 2 to 3 types. So then squeezing criteria, Hong-Mendel squeezing criteria, Vogel criteria, of all these directly or indirectly, all are. If once all these things are satisfied, that particular light, that particular state will show the non-classical nature. Wigner function, Wigner volume, optical topogram. So all these are the mathematics. It is not justified to explain all these mathematics in such type of talk, but yes, these are the mathematics which can be calculated, which can be understand, and with the help of such kind of mathematical things, we can understand the world of non-classical phenomena. These are our results for a particular state. Like here I have to say NGBS. This is basically generalized binomial state. Binomial, as you already know that, like Poissonian is a distribution. Similarly, binomial can be a distribution. Binomial which basically covers 2 extreme limits. For some values that can be 0, for some other values that can be 1, or that can be in between. So basically there are many distribution systems within the light. Light can have so many types of mathematical distributions. For example, binomial distribution, negative binomial distribution, reciprocal binomial states, geometrical states. There are so many number of states. तो जिस तरह से बहुत सारे criteria हैं, similarly we have so many number of states too. Just we have to apply over them, and with the help of that application we can do that. And within all these results, the things are common, like this is the criteria of higher order, means L is equal to 2. For that L is equal to 2 means basically this is D3. So D3 and their value comes out negative. So there is basically like minus 1000, minus this. So this whole these things are negative, और negative का मतलब lesser than 0. तो मैं वापस एक बार इस criteria पे आता हूँ. Yes, this was the criteria. Within this criteria, this D should be lesser than 0. If this satisfies, state shows anti-bunching. If this comes positive, state will not show anti-bunching. So for example, these are the things. What about R1, R2, R3, R and Q? Obviously, this R, Q are the parameters of these states. Where R photon added, T photon added. Yeah, means ये भी एक अपना में बड़ा interesting part था कि I can have a particular distribution and that can be photon added too. With the help of the photon addition or subtraction, we can get it. R135, T, and so on. But overall, within these results, at least for this audience, I just have to say, all these results are satisfying the criteria, and once they are satisfying the criteria, they are definitely anti-bunched. More or less correspond to the parameter. Similarly, our other results, like these results, shows sub-Poissonian photon statistics. We will not go in much detail of this, but yes, there are some criteria if they are showing. Obviously, in many criteria we got this positive value, but there is no meaning to show over here at least. But within our paper, you can read the things is within certain conditions they can show positive too. So then, what will be the utility or what will be the importance of our work? Our work will justify. Our work will show the detailed analysis of a particular optical light that within these range, within these parameters, within these conditions, the light will be non-classical. So this is Poissonian. Similarly, Mendel Hillary type switching, higher order switching results. For example, within these results, we can understand these are negative, but here we have to say within a particular range of P and Q and R or T, this shows negative, but other results are positive. It means higher order squeezing, Mendel higher order squeezing is weak and shows within a permissible range only. So this is basically the mathematical analysis, which is highly useful for the experimentalist. Similarly, the other result, this is the form of the Wigner function, where this is a two-dimensional graph, and within that graph, this color variation can show the depth, can show the negativity corresponding to a particular level. For example, here 0.0198, but for this color, at least for this dark color, this comes out negative. So that is interesting for us. Similarly, here there is the range above this range, this is the positive, below this range, this is the negative, and so on. So this is the effect of, or this is our study related to the photon addition and subtraction over a particular state. Optical tomograms, again, there is a big research, but overall, all these results supports our claim for non-classical states. These are our publication, higher order non-classicality in photon added and subtracted fluid states. Similarly, the another publication, this the Kathakali Mandal was my research student, which has just finished her PhD within the domain. Other papers with Professor Patak, our group. Now, what about ongoing project? We have an ongoing project funded by the Department of Science and Technology, and with the help of this particular project, we are in early stage of the experimental quantum information. Soon we will have our, obviously we have purchased so many things like big optical table, lasers, all supported optical things over the bench. We have the QKD systems too in our lab, and this is a project funded by DST under the scheme of ICPS, Quantum Information Science and Technology Program. Professor Pathak is PI, I am co-PI, designing of devices and protocols for quantum hacking, random number generation, and secure communication. This is a group photo of our past students, some current students. Here is so basically we have a group page, Quantum Optics and Information Group, JIT. You can search over the Facebook too. Here is the Professor Pathak and myself. I was his first student, and later we have a big group, and our students are abroad too, like Kishore is in Czech Republic. Other students, Nasir, now a faculty, Chitra Sukla in China in the Quantum Information Group, Abhishek, and many more. What about our university? This is the Sector 62 campus. Big auditorium, learning resource center, the main academic building with hostel facilities. This is our extension campus at Sector 128, Chief Institute of Information Technology. And these are the pictures related. Thank you so much. If you have any question, you can ask.
Any queries from the participants? Any queries? You can write your queries in the chat box. After that, I'll unmute you if you want to ask anything. Or you can raise your hand.
Okay, it's fine. The majority is from the
Computer science background, basically.
that's why I have not explained the much technical details, much mathematical criteria. My point was to just explain where this particular field lies and what are their importance in quantum information theory or quantum computing, and how our research support that particular thing. Obviously, this
Yes,
is quantum itself computer science facility is very big. There are very less people who
actually, you are right, because the quantum has its origin from the physics only.
Exactly.
So, like the computer scientists, they are trying to learn, right? And you really have given a deep insight of the topic, right?
Yes,
So
I'm
sure participants must have learned about the new arenas, right?
Exactly.
So how it has originated. So it was really very well delivered, and we are really very thankful for being here and agreeing to be the part of our summer school. Thank you so much, sir. It was really a wonderful session.
Thank you, Professor Mehta, for inviting me.
Thank you, sir.
Okay.
So we will have a 15 minutes break, and then we will start the session again after 15 minutes.
Oh.
Rohit, can you hear me?
Yes, ma'am.
Now you can unmute and you can also try out sharing.
Okay. Do I need to switch on my video?
Maybe in the beginning, later on, it is your choice. And if
Okay.
you switch it on, it's better. It seems live to the participants.
Okay. My screen's visible, right?
Yeah, it is visible.
Okay. So PPT is also visible.
Yeah, it is visible.
I'll check out the work.
Yeah.
It's visible. So,
Yeah, it is. Yeah, it's working fine.
Okay. And then it's fine.
Yeah, then it's fine. So we will start the session after 10 minutes, right?
Okay.
Okay. So we are about to start the session. Mr. Rohit?
Yes, ma'am.
Yeah, you're there. Yeah. Okay. I welcome you all to the day 5, session 2 of the summer school on quantum computing and applications. The speaker for the day is Mr. Rohit Chaurasia. Mr. Rohit did his BTech in engineering physics from Delhi Technical University. Currently, he is working at QLab Software Limited. He is part of the Quantum Digital Simulation Group. And before joining QLab, he has worked with Tech Mahindra Makers Lab, Pune, Curious Technologies Private Limited, Hyderabad. He was a winner of the Community Choice Award for the Hackathon project Quantum Orchestra. We welcome you, Rohit, and request you to start the session.
Okay. Thank you, ma'am. I'll share my screen.
Yeah, sure.
Visible, I guess. So, okay, I'm Rohit. Ma'am gave the good introduction of me. So, I'm Rohit Chaurasia. Right now, I'm working at Q Labs as a research intern. I'm working at Q Labs as a research intern. I'm there working in a group called the Digital Quantum Simulation, where we are trying to simulate some natural phenomena using the theory of digital quantum simulation. So today I'll be giving a small tutorial on what digital quantum simulation is, and also work out the simulation of Heisenberg model on a using a whiteboard. So I think we can start.
Yeah, sure.
Okay. So content for the day. This is the content. I'll be starting with a small introduction to the simulation, what simulation is and why is it important. Then I'll be having a I'll show some limitations of classical simulators, that is normal classical computers that we have, and how they are limited. Following, we'll be talking about the quantum simulators and how it was, like where the idea came from and what all are the advantages. And these quantum simulators are broadly divided into two aspects. First is digital simulation, and then we have analog simulation. So I'll be discussing what they are and differences between them. Following that, I'll move to my whiteboard and I'll be showing Trotterization. The concept I'll be introducing a concept of Trotterization. So this is an important concept that is actually used in digital quantum simulation. After that, we'll work out the digital simulation of XZ model. So basically, XZ model is a specific type of model which is derived from the Heisenberg model. Heisenberg model is a kind of more uh, general model. So then I'll show some simulation results that we have performed, and we got the results for that. So what is simulation? So over here, I've written that it is defined as artificially reproducing the properties of dynamical evolution in time of any other natural phenomenon. So what do we mean by artificially reproducing the property is that we are choosing a particular system that we have a control over. And then on that system, we are trying to recreate or simulate the properties of the system that we want to understand. For example, we can take for example a solar system. So we want to simulate the solar system, and for that what we do is we create a model, a mathematical model, and then perform that perform the computation for that mathematical model on our normal computers. So those normal computers are electronic systems. So basically what we did over here, we simulated a solar system in using a electronic system. So this is known as simulation, and it is a very old field, and it, like, over the centuries there has been a huge development. So few of these methods that have been developed for simulation are Monte Carlo methods, molecular dynamics, tensor networks, etc. Also, the physical these are the three steps that I have mentioned, which are important, which are followed during simulation. So the first is the physical system. So we select the physical system that we need to simulate, and we gather all the information that we need about that we can have about that. So then we move on to the second step, which is modeling. And so modeling is basically mapping the information that we have to a set of equations and variables. Now, those set of equations and variables uh, result in an analytical or a numerical solutions. So, result, we get an analytical and numerical solution to the set of equation and variables. So these analytical and numerical solution are called the simulator. So basically, once we have the analytical or numerical solution to the problem, to the set of equations and variables that we created, we compute that for certain value of, let's say, for certain time instant t. We used the expression from the analytical or the numerical solution and perform computation on a computer. So that computer is called a computational device, and these analytical and numerical expressions or the solutions that we get are called the simulator. Or you can say that these mathematical identities are termed as simulator. Then there are a lot of limitations to the classical simulation right now. If you talk about the field of quantum mechanics, where we are talking about the study of small particles at a quantum level, there these particles manifest various quantum properties like superposition. So let's say one particle can be superimposed into two states simultaneously. So in order to define one particle, we would need two variables because it has two states. Then similarly, if we need to simulate n quantum particles, we would need 2 to the power n variables. So if a scientist is trying to simulate 100 quantum particles, he would need 2 to the power 100 variables. This is, which is actually out of reach of even many supercomputers in today's date. So 2 to the power 100 is a very huge number, and we do not have that much memory. So we see that when we are going down to the quantum level, we find that there is an exponential rise in the requirement of the resources, which currently the classical computers cannot fulfill. So in 1982, Richard Feynman, he proposed the idea: what if we have a controllable quantum system? So what if we have a controllable quantum system? We can actually simulate the concerned quantum system that we want to understand or we want to know its properties using a controlled quantum system. So what exactly is a quantum simulator then? Uh, so basically, it is a system that over which you have a very high control, and you can use this to reproduce some other quantum physical systems, irrespective of their degree of correlation or entanglement. So basically, then you are actually trying to simulate one quantum system using the other quantum system. The only thing is you must have a good control over the quantum system that you are using. So there are two routes for the quantum simulations: digital and analog quantum simulation. So I'll discuss about analog and digital. In analog system, you are doing the same thing. You are simulating one quantum system using the other quantum system. But in this case, the other quantum system is reproduced using of like a set of externally controlled parameters. So these parameters can be your electric field or magnetic field or something else. The problem with this analog type of quantum simulation or quantum devices is that they can simulate only a particular kind of systems. For example, if you have a bosonic analog system, quantum system, they won't be able to simulate your fermionic systems. Basically, bosonic system are the ones which have particles involving spin, integer spins, plus minus 1, plus minus 2, plus minus 3, while fermionic systems are those systems having integral multiples of some half integers, half fractions. So it is not possible for that analog bosonic analog system to simulate the fermionic systems. So this is one disadvantage of the analog quantum simulation. Now moving on to the digital quantum simulation is a general purpose quantum device. So it is able to reproduce any system that you have, any quantum system that you have, as it actually uses the Hamiltonian of that system and then translates it into a sequence of quantum gates. Now, the important thing to note is that these quantum gates are special because they are universal. So basically, once you're able to encode your Hamiltonian into the sequence of quantum gates, since these quantum gates are universal, you will be able to simulate using or simulate or implement these quantum gates or the sequence of these quantum gates on various different quantum systems. That is one advantage of digital quantum simulation provides us. This is what I have written over here. Since the Hamiltonian is translated into a set of universal quantum gate, it can simulate any target or system model. So what are the processes which are involved in this digital quantum simulation? First, you need to know the physical system that you want to actually study, and then you take the Hamiltonian of that system. So you describe the target system or the model, the Hamiltonian of the target system, and then let's say you want to simulate it on a superconducting qubits. Now you're trying to simulate a quantum chemistry problem, let's say a chemical reaction. So that chemical reaction at a quantum level involves fermionic systems, and superconducting qubits are based on spin half particles. So in order to have like in order to be able to simulate, so basically fermionic systems have annihilation and creation operator, and these spin half systems are based on poly sigma poly algebra. So there has to be a link between or translation between this algebra of annihilation and creation operator with this poly algebra. So those methods are called mapping methods. So after we do the mapping, next thing that is done is check for the trotterization. So I'll explain trotterization in more details later. So after trotterization thing is done, and then you actually exponentiate your Hamiltonian to get a unitary, and from that unitary you can actually get a sequence of quantum gates. So there's your quantum algorithm, then the sequence of quantum gate. Now you can just implement these sequence of quantum gates are parameterized, and therefore you can implement them for different time instances at t equal to 1, at t equal to 2 seconds, so on. So I'll give a very small explanation of a brief revision of quantum mechanics. So sorry. So in quantum mechanics, you have these kind of linear differential equation. It is known as time dependent Schrodinger equation. So we know that the first equation above here gives the solution to the differential equation, general solution, which is a vector x at time t when operated by this operator is given by the this particular operator operated on the initial vector. So similarly, we have a solution. The wave function at any time t is given by this unitary operator operated on the initial wave function. So once you know the initial condition, you can know the state of the wave function or the vector at any time t. So over here, this term exponential e to the power minus iota ht is called the unitary. It is a unitary operator, and this h is the Hamiltonian of the system. So I've been saying Hamiltonian a lot. So what is Hamiltonian? Hamiltonian is nothing, like if we put it in a very simple language, it is nothing but the total energy of the system. That is the kinetic energy plus the potential energy. So I'll right now move on to the whiteboard to explain the concept of trotterization. If there are any questions regarding this, right now what I've explained till now.
Any queries till now? Anyone having any query, you may ask any time. You can write your queries in the chat box also, or you can raise your hands. I think you can continue.
Okay, ma'am. So I'll continue. So in 1982, I said Richard Feynman gave us an idea. He proposed that any quantum system that we have, which can be controlled, over which we have a control, can be used to simulate other quantum system that we want to understand or study. So so once we have this controllable quantum system, we can actually simulate any target quantum system. Now, this was just a proposal or just an idea, an abstract idea given by Richard Feynman. In 1996, Seth Lloyd, he proved that this is actually possible, but there is restriction that this controllable quantum system won't be able to simulate the real or target quantum systems accurately. Not all the time. Sometimes it will be, but not all the time it won't be able to simulate it accurately. So there will be certain approximation. So he proved this thing, and then this is actually because the Hamiltonian is written as the sum of the local Hamiltonians. So what is local Hamiltonian? Let's say we have a box and we place two quantum particles inside them, particle 1 and particle 2, and we have an electric field E. Now, how would you write the total energy of the system, total Hamiltonian of the system? Basically, it will be the total total energy of the system. So we can write it like this. First, we move to the particle 1. We write its Hamiltonian H1, which is sum of its potential energy plus the sum of its kinetic energy. Then we write the Hamiltonian of the particle 2, and which is nothing but the potential energy plus the kinetic energy. Then there's an electric field that is applied externally. So this electric field applies certain interacts with these particles in terms of some force and provides them with some potential. So it is also providing some energy, right? So we can write the Hamiltonian of this due to the electric field, which will only contribute to the potential energy due to electric field. So these H1, H2, and H3 are actually called the local Hamiltonians. And when you sum up all the local Hamiltonians doing a summation, you would get a total Hamiltonian of the system, total H. So this is the concept of local Hamiltonian. So all the quantum systems are described in terms of local Hamiltonians. So using this, this is a concept which we'll be using, and we'll be showing Trotterization, explaining the concept of Trotterization. Okay, so before understanding Trotterization, one should have a knowledge of what commutation is. So commutation relation is defined as between two mathematical operators, basically two matrices, let's say H, L, and HM. This is the square. If you put them in a square bracket, then it means that HL times HM minus HM HL should give you 0. If this thing, this left hand side is equal to 0, then you say that HL and HM actually commute. So you say that they actually commute. Now we'll be using a mathematical identity. Since these Hamiltonian that we have, HL, these are not scalar. These are not scalar and not even vectors. They are matrices. They are operators. In mathematics, when we apply, let's say we have a vector X and we are applying a matrix M on this, then we get a new vector X dash. So this application of this matrix on this is known as is called operating M on this vector. So similarly, these Hamiltonians are actually operators, quantum mechanical operators. So we need to deal it in a different manner. So we use something called Suzuki Trotter decomposition. Suzuki Trotter. Yes, decomposition. So let's say you had a Hamiltonian. H was written as sigma of all the local terms. You can create a unitary operator by exponentiating it like this, HL times t. Now this is nothing but the solution of the differential equation that I had shown earlier in the PPT. So I've written it like this, but using Suzuki Trotter decomposition, you can actually write this as u is equal to this exponent minus iota sigma HL t can be written as limit n tends to infinity. You have product L equal to 1 till L e to the power minus iota HL t by n and the whole to the power n. So now there are two conditions that we need to study. First is if the local Hamiltonian HL and HM, let's call, there are like capital L number of local Hamiltonian terms, right? So if they commute to 0, that is they are equal to 0, then we can put n equal to 1 and we will get our normal u as this, L equal to 1 to some L. So this is a very normal thing. This is what is the unitary, and we'll be decomposing this in terms of quantum gates later. But if they are not equal to 0, if they do not commute, then we need to choose an arbitrary value of n which is very large. Like since n is tending to infinity, but we cannot choose n as infinity. This is not possible for us. So we choose it to be a very large number, and therefore we get a approximate unitary that is approximately equal to product from L equal to 1 to L exponential of minus iota HL t by n capital N. Okay. So if we call this part as u, what we are getting over here is u dash is approximately equal to u to the power n. Now this u to the power n, if we recall in the PPT we had the differential equation like this. Initial wave function psi naught applied u, and when we apply this operator, unitary operator, we would get, in this case we would get approximately the wave function at particular time t. Now this is u dash, we can write it as u to the power n approximately, and we write it like this, we would get this. So from here we can see that u to the power n can actually be expanded as u multiplied by u so on n times, which would give us psi of t, approximate psi of t. Now we are going to decompose the unitary u into a quantum circuit, right? So what this means, we are applying this particular quantum circuit n number of times on this initial state, which gives us an approximate state or the wave function at the end. So basically, what is the takeaway from Trotterization is that whenever we want to simulate some Hamiltonian, we need to check if the local Hamiltonians actually commute or not. So if they are commuting, then we can simply work out one circuit and it will be done. But if they do not commute, then we have to choose a very large value of n, and repeat that circuit n number of times to get more accurate results, more accurate final wave function. Larger the value of n, the larger will be the the better will be the approximation. So next thing that we have after Trotterization is moving on to the model that I was talking about. So I'll be describing the Heisenberg model right now. So over here, let's just, so we will be using Trotterization later. So Heisenberg model. This is Heisenberg model. So what is Heisenberg model? It is nothing but a system of particles or spin particles, basically, which have spin, which are arranged in different ways, like in different orders. So broadly, there are three kinds of ways that you can arrange these spin particles. First is, let's say first is this. Let's say all particles have spin up, spin up, spin up. This is called 1D chain, a 1D chain. And then let's say we have particles arranged like this in 2 dimensions. So we have 2D chain. Similarly, we will have a 3D chains where particles are arranged in a cube or sphere or whatever shape we want. So this is called a 3D chain. Right? So okay. So I'll be considering a very simple 1D chain and explaining everything from there. So let's say we have spin up of the particle, which is defined as ket 0, and spin down is defined as the state ket 1. We are just given it the notation so that we can represent it in quantum circuits, right? So these are nothing. So how do we write the Hamiltonian for the complete 1D chain? So let's say we have two particles which are arranged in 1D chain like this. So there are two things to it. First thing is that this particle, let's say we have one more particle over here. This particle will interact, the spin of this particle is going to interact with this particle, and this particle is going to interact with the spin of this particle. So what we call this is a nearest neighbor interaction. So we are going to define the Hamiltonian for this nearest neighbor interaction. So let's say since the spin, so this nearest neighbor interaction can happen in 3 coordinates. Alpha is equal to x, y, z, right? So accordingly, we can define, so this particle is going to interact with this particle, right? This is particle 1, this is 2, this is 3. So particle 1 is interacting with the particle 2. So we would write it as sigma x. Let's say we are talking about interaction in x direction. So we'll write it as particle 1 sigma x tensored with particle x in second particle sigma x. But the second part, we are considering the interaction between these two. So we do not take this into account. So we just put an identity over here. The third on the third particle, we are applying identity operation. Plus, now we consider the interaction between 2 and 3. So the first particle becomes identity, and then the second particle becomes sigma x uh, 2 and sigma x 3. So we are not constrained, like we are not constrained that this particle interacts with the first particle. We are just not constrained that, because that would give us a not a linear chain, but that would give us a cyclic chain. We are going to work on a linear chain. So mathematically, linear chain is this particle interacting with this and this with this. So this now, based on how close these particles are, the strength of interaction will be decided. So if they're very close, then their strength of interaction will be very high, very high. If they are very far away, then their strength of interaction would be very less. So we can use a particular parameter called J, and for X, since the interaction is in X direction, we use Jx. So this defines the strength of the interaction between two particles. Let's say they are on equidistance. So Jxx would be equal for all for these two couples. So we have Jx. We can write this as Jxx. So this gives us the interaction in X part. Similarly, we can have interaction in Z as sigma Z. I'm not writing the particle number. That is, I think, understood that the position of sigma defines the particles that we're operating on. And then sigma Z, sigma Z. Similarly, we have interaction in terms of poly y, JYY. So in the y direction, we are talking about y direction now. So sigma y identity plus identity y y. So when you add these all up, you're going to get the Hamiltonian for the nearest interaction. So which can actually be simplified and written as like this: H nearest neighbor interaction NN, which I'm denoting as NN, can be written as sigma JYY JYY sigma y plus ith particle on I plus 1 particle, ZZ sigma z on I plus 1 particle, I plus 1 particle, plus JYY on sigma y I particle, sigma y I plus 1 particle. Sorry, this will be I. Okay, so this is what is the Hamiltonian for Heisenberg model. Right, this is the Hamiltonian for the Heisenberg model, and we are going from I equal to 1 to 2, or basically the total number of particles minus 1, right? So okay, so this is one equation one. Let's call it equation 1. Now, since we have 3 particles, and what if we introduce a magnetic field? This is in z direction, z direction, z direction. We introduce a magnetic field in x direction. So what will happen? The spin of this particle will interact with the magnetic field H in x direction individually, and this will interact with this, and the spin of this will interact with H, and spin of this will interact with H in x direction. So these spin particles will individually interact with the magnetic field. So this is known as self interaction. So we need, if you are introducing a magnetic field, then we need to write the Hamiltonian for self interaction as well. So Hamiltonian for self interaction is simply can be written by the magnetic field strength times the it will be sigma x, and this field is interacting in the x direction on the particle I. Rest we do not consider. as we consider them I, because we are talking about individual interaction. Then we talk about the second particle. So we position the sigma in the second position. And then when we talk about the third particle, we position the sigma x in the third direction, in the third position. So in a compact way, you can write it as sum I equal to 1, 2, 3 particles, sigma x. Ignore an I, we know how, but depending on the particle we are talking about, the position of sigma will differ. So just ignoring that I, we do not need to write that. Okay, so this is equation 2. Now, so I had mentioned XZ model, something called XZ model. So what I am going to do for XZ model, it means that we have an electric field, the magnetic field in X direction, and then we only have the interaction, nearest neighbor interaction between spin in only X coordinates, in Z coordinates. So in order to have zero interaction in X, this should be X. I write it over here correctly. So in order to have interaction only in Z direction, these two terms, the YY and XX interaction must vanish. How can they vanish? It's simple. We should have JXX equal to JYY equal to 0. So if they are equal to 0, these two terms will become 0, and finally will actually be left with the new nearest neighbor interaction term, which is JZZ, sigma Z I, sigma Z I plus 1, from I equal to 1 to 2. In our case, the particles are 3, so we are counting interaction. So particles are 3, so we have 2 couples. We are 2 pairs, so we are having the sigma going till first to the second pair. So this is the nearest neighbor interaction only when with ZZ interaction. And we also have a self interaction term, which we know is H sigma X I equal to 1 to 3. So basically, if we have excluded the interaction of spin in X and Y coordinates, and we have introduced a magnetic field in X direction, what we get is the sum of this over here, this Hamiltonian plus this Hamiltonian H self. So we can write it as sigma xi plus jzz sigma jz I sigma jz I plus 1. Okay, so basically what we have got here is the Hamiltonian of a very famous simple model called TFIM. This is transverse field Ising model. Okay, so so basically, if you turn off the interaction in XX and YY direction and have a magnetic field in X direction, then you get a TFIM model. So for TFIM model, we can picture it as like this: two particles like this with the magnetic field in the X direction, having a spin in Z direction. So the system is described by this particular Hamiltonian, right? So now we will be actually translating this Hamiltonian into sorry, into a quantum circuit. Now this part is very interesting. Okay, so first we start with the part one of the first term of the Hamiltonian that we have created, this, which is the self interaction Hamiltonian. I'll write it down over here that h of self interaction is actually given as h sigma x on ith particle. Now you know that unitary is defined as when you have you exponentiate the Hamiltonian to get the unitary operator, which is nothing but the solution to the time dependent Schrodinger equation. This is the Hamiltonian. Now we need to plug in h self over here instead of h. So what we are going to get is u is equal to e to the power minus iota h sigma x I times t. So I equal to 1 to 2. So now for this, now I'll be performing some calculations, and for the sake of simplicity I am just using two particles right now, right? So I equal to 1 to 2. So you can just expand it. You can write it as minus iota h sigma x particle 1 times t multiplied by minus iota h sigma x particle 2 times t, right? So, or more in a more compact way, we can write it as I equal to 1 to 2 e to the power minus iota h sigma xi times t, right? Okay. So we need to create a circuit for this particular unitary, right? So there is one famous there are three rotation gates which are very famous, which we know of, and are universal rotation, are called are universal rotational gates, which is mathematically defined as r of alpha theta equal to e to the power minus iota theta by 2 sigma alpha, where alpha is a set of x, y, z, right? So what it means that r of x theta is nothing but e to the power minus iota theta by 2 sigma x. So this defines the rotation of the state vector that we have, state vector in x direction, right? Similarly, we have ry and rz, which define the rotation in x, in y and z direction. So if we see, we can see there's a similarity in this equation and in this equation. So we can just compare them, right? On comparing, you would find that if you were to compare them, we would get e to the power minus iota theta by 2 sigma alpha equal to e to the power minus iota h. It was sigma for ith particle. We are considering for the ith particle, so we put I over here. Sigma x times t. Now since we are having sigma x over here, we can take alpha as alpha equal to x, and then we would get that we would get that theta by 2 sigma x ith particle, sorry, h sigma x ith particle t. So what we see over here that theta, the parameter of the rotation gate, is basically theta by 2 is basically h times t. So theta becomes twice of h of t, right? So basically we had this equation, right? This equation number 2 over here. We can then you can actually rewrite it in terms of rotation gate. The unitary then would look like product from I equal to 1 to 2 r of x rotation gate, where theta is equal to 2ht. So now we have written the complete circuit. We have written the unitary in terms of the Rx rotation gate, right? So Rx rotation gate. So if you expand this, we can write it as Rx theta equal to on the I particle always. So theta on the R1 first particle multiplied by Rx for theta equal to 2ht on second particle. Okay, so these are rotation gates, Rx gates, and we can easily implement them on a quantum circuit using various simulators like Qiskit, and there are many, Circ or something else. So so we can write this, right? So this was our configuration that we were considering, right? So this is in up direction, so we had chosen this notation that up is 0. So we have initial state as 0, 2 qubits, let's say. On to the first particle, we are applying an Rx gate. So we write over here Rx theta equal to 2ht. And on the second particle, we are also applying the same thing, second particle Rx gate 2ht. And here what we have is this is actually, we have actually implemented the circuit for self interaction Hamiltonian. Right now, we need to implement this complete Hamiltonian that we have here. This complete Hamiltonian, right? The first term was the self part, and the second one was nearest neighbor interaction. Now we want to implement the nearest neighbor interaction. So in the nearest neighbor interaction, where is it? Yeah. This part of the next part of the circuit would be nearest neighbor interaction circuit. Okay. So the nearest neighbor interaction circuit, we had the Hamiltonian as HNN, nearest neighbor, as JZZ, sigma Z1 tensored with sigma Z2, right? Since we are considering only two particles, this would be the net Hamiltonian that we are going to get. Now we have to repeat the step. You have to get the unitary, which we will be getting by exponentiating it, iota HNN times t, right? Which is nothing but minus iota JZZ Z tensor to it. So I'm not writing this notation right now because we have only two parts. Is for the second particle. So we have got this. Now we have to implement the circuit for this. Now there is one more identity that we'll be needing to implement this particular circuit for this, which is minus iota delta sigma z tensored with sigma z is given as this circuit, or implemented by using this circuit R of Z 2 delta. right? And here we have C naught 1%. Okay. Right. This is also known as ZZ circuit. So if you had studied some quantum machine learning, you would find that this ZZ, XX, and YY are there. These are also used as ANSATs over there, right? To implement to do a feature mapping in order to do a feature mapping. But right now you can actually prove this. You can prove this using expansion identity, which says theta times a matrix M is given as cos theta times identity plus sine iota sine theta by 2, sorry, theta by 2 times the matrix M. So instead of matrix M, we need to plug in this matrix, and then you will get a 4x4 matrix. Since it's a two particle system, we will get a 4x4 matrix, and you can then decompose this matrix in terms of C naught and your C naught and your rotation RZ gate, which will be like this. So I'll just redraw that. So the rotation, so our unitary was this minus iota j z z z z, or sigma z insert with sigma z, which is given as rotation z twice of delta rotation z. This is a circuit for this. So in our case, the 2 delta would actually be equal to z z z. So delta becomes z z by 2. So we are able to implement this the self interaction term. This is a self interaction unitary. Sorry, nearest neighbor interaction unitary in terms of a parameterized circuit. Okay, so next thing is that I'll mention two more identities are there. One is minus iota, let's delta sigma x sorry x x, and there is also sigma minus iota delta sigma yy. So these two are can be written in terms of sigma y, in terms of using this circuit. So basically, how do you write it? You have a particular, you write it like this. So sigma x, you have this particular identity. That again, one more identity we have sigma z, which is sandwiched between rotation y gate with angle equal to pi by 2 sigma x, right? And we will have rx pi by 2 so x pi by 2 sigma. Okay, so basically what you're going to get over here is that you put these identities, these two, into over here, and you will get something like this. Is going to be a huge expression. Ry gate, let's assume that ry is rotating at the angle of pi by 2. Insert with ry multiplied by z ry. So these are interaction. So the circuit for this actually can be written as this part applies on the particle 1 or qubit 1. This applies on the particle 2 or second qubit. So the circuit would look like somewhat like this. You have initial states of two particles, then you apply this on the first qubit, which is ry rotation. You apply sigma z, right? And then you again apply ry. Now when you talk about the second qubit, you apply ry, then you apply sigma z, then you again apply Ry. Right now, this part over here is actually sigma z tensored with sigma z, and we know the circuit for sigma z tensored with sigma z, which is this is the circuit, put the same. So we can write this circuit as again as some ry gate at pi by rotated by pi by 2 ry gate, and now we will implement sigma zz over here, replace this block by sigma zz circuit or zz interaction circuit. Over here we get rz 2 delta, right? 2 delta. And then ry, then again one more ry. Okay. Right. So this would be the interaction term for xx. So this is called xx interaction. In a similar way, if you replace y with x over here, you would get y interaction. So in our Hamiltonian that we did, we actually took these interaction jxx and jyy equal to 0, right? So this means that if we would have not taken if they were not equal to 0, we would have to implement this circuit as well. For the simplicity, I have only taken jzz. One can actually take all three and create a circuit using them. So okay, so back to the circuit. So we know the circuit for zz jzz. So we will basically write it as write our next circuit, complete our circuit as this. So here we had self interaction part, which was Rx 2ht. The parameter becomes 2ht. Then we have Rx 2ht. Right now, this was a self interaction term. So I'm putting a barrier over here. The self interaction is done. Now nearest neighbor interaction, which was ZZ interaction only in our case. So for ZZ interaction, we know the circuit, we have derived it right now, or we have taken it for granted, like we know that is the identity. 2 delta, it was 2 delta, so we would write it over here. Delta, and delta was equal to j by 2, jz by 2. So we would get over here the parameter would be jz. So this is the self interaction part, and this is the nearest neighbor interaction part. So finally, we actually have completed the circuit. And okay, so initial state is in 0, 0 because our configuration of the 1D chain of the spin particle is somewhat like this. So this is 0 and this is 0. If we would have taken the configuration like this in downward, then the initial state would have been 1 and 1. We would have got 1 over here, 1 over. We would have started with 1 and 1, or we might have put an x gate over here to get that, to get this state. So it doesn't matter what state we start with. Okay, so we have got the circuit. This is the final circuit for our Hamiltonian of TFIM that we are discussing right now. Right now, there is some important property that we must know about TFIM. There is a reason why it is famous, and I'll tell you the reason. Classically, when you treat these two particles which spin up from classical point of view, what you will find is that there is no phase transition. What do I mean by phase transition is that when all the particles are aligned in the same direction, that is called a ferromagnet, right? So this chain of two particles in the same direction is a ferromagnetic chain. Now, over time, experimentally, it is observed that over time, what happens is that given certain amount of time in an external, when you apply an external magnetic field, these spin will become randomly aligned. So if they are randomly aligned, then net spin would be equal to 0. So let's say spin up has a value of +1 and spin down has a value of -1. So the total spin over here would be +2. And now after given time t, the net spin becomes 0. That means one of these particles, spin of one of these particles actually flips. So let's say the second particle flips. Now it will be +1 -1, which is 0. But classically, we do not see this phenomena. This phenomena is not predicted by the classical approach. But when you solve the situation using the quantum mechanical models, there is a prediction. It predicts this phase transition. Right? And there's a particular graph that you get. So that graph is somewhat like this. It goes like this. So this is the maximum spin, and here you have the minimum spin, maybe 0 or maybe very small value 0.0001 or something, right? And this is time t, and this is the total magnetization, right? So quantum mechanically we must observe this phenomena. Now if we have created the circuit, why not we measure the properties, this magnetization property? This magnetization is actually can be given in quantum mechanical term, is given as the expectation value of sigma z divided by the normalization constant. Sorry, there will be a sigma. So expectation value of sigma z of the first particle plus the expectation value of the second particle or sigma z divided by normalization constant n, right? So this is the magnetization. So we can actually calculate the expectation value of z by just simple measurement. We just need to apply a measurement operator over here, right? And applying the measurement after we measure in z basis, we will be able to calculate the expectation value of sigma z of first qubit and of the second qubit. So we then sum it up together to get the total magnetization and divide it by the normalization constant. So this gives us the total magnetization of the particle. Okay. So once we have done this, so this was the main purpose of digital quantum simulation of simulating TFIM. We must observe this particular nature of the curve once we are simulating it on a quantum computer. So I'll show you the code that I have and my friend wrote together to implement this model on a quantum computer using digital quantum simulation. So this is the code that we have written together. You can see over here. So this is the initial mathematical concepts that I have explained earlier in the presentation itself. So we have used Qiskit to implement this model. Over here, you can see we have defined some constant like Planck's constant, the JZ value, JZZ value, and this frequency is when you are taking the magnetic field.
Rohit, so you execute this code on your classical computer only?
We have executed on a real IBM computer. We have executed on a simulator, and we have done also compared it with the classical simulation methods. So I'll show the results also. So over here we are create this function creates the quantum circuit, evolution of the quantum circuit. So yes, I wanted to mention one thing. This final circuit that we have, we can just plug in the value of, let's say we have a constant h, we can plug in the value of as t equal to 0, we'll get magnetization at time t equal to 0, and then t equal to 1, we'll get magnetization at sigma 1, and t equal to 2, we would get similarly magnetization at 2, so and so on, right? So this is what we have done. We have created this circuit sorry, and we have just plug in the values of different values of t inside it. So this is the circuit function that we have created over here. It returns the circuit. Now we just visualize, in order to visualize, let's say we have 2 qubits. So you can see over here in the circuit, you would see this particular first part is actually the self interaction term, and this is the nearest neighbor interaction term, right? And the second, let's say for 3 qubits, if we had 3 particles aligned in the same direction initially, like this, right? So this would be 0 0 0. Initially we would have 0 0 state. So what would be the case? Now this is the self interaction part. The first part over here is the self interaction part, particle 1, particle 2, particle 3. Now this part is the nearest neighbor interaction. So the particle 1 interaction interacts with particle 2, and the particle 2 interacts with the particle 3. So we have, so this is the circuit like this. If we had 4 particles, then we would have one more cascade. We would have a cascade of this part. There would be an interaction circuit for particle 2 and particle 3 and particle 4, right? So this is the unitary operator that we have just numerically calculated this using the code itself. Now on the back end, we have built the circuit and performed mapping and run them. So here, like after some processing and calculating the average magnetization using this particular function of called magnetization, we created this function over here, average magnetization, and before that. Okay. So this is the relation. This is the thing. This is a result that we are getting on a real quantum computer, and sorry, this is the result we are getting on a simulator. So you could see that initially it starts with the magnetization equal to 1, and then it slowly over the time t, it starts to decay and the magnetization tends to 0. So the nature is same as predicted. Okay, I'll move in the slides. Okay. Okay, so you could see this. This is the result from classical simulation, and this is the result from our quantum simulator. So you could see we are able to get the quite correct result, right? So basically, we were able to implement the TFIM model, which is a simple model. Not only TFIM, we have also implemented full Heisenberg model. In that case, you need to perform Trotterization. In this case, we did not perform Trotterization because the local Hamiltonians, they commute. But when you apply, when you are implementing the total Heisenberg Hamiltonian and you introduce a magnetic field term, then you have, you check, after checking the commutation relation, you will find that many of the local terms do not commute. So in that case, you have to perform Trotterization. But in our case, in TF5, we did not need to provide that or do the Trotterization. So yes, we were able to get quite good results. There is exact. This is actually because we have taken larger time steps t. If you would have taken a smaller time step, you would got more precise relation. But since we do not have that much time on IBM's quantum computer, So we only get we are only able to run only a small number of time steps. So yeah, so this is the result. And if there are any questions, I can answer.
Any queries from the participants? Any queries? You can write in the chat box or you can raise your hand.
Rohit, which simulator you use for quantum simulation?
We have used Qiskit. Sorry. We have used Cosm.
Pardon?
We have used Cosm simulator for simulating this.
So this is provided by IBM.
Yes, it's in the package of IBM only.
So anybody can access it.
Name of that. Can you write name of that on in chat box?
Yes, sure.
हाँ बताओ वो चलेंगे.
And is this freely available for everybody can use it?
Yes, it's available for everyone. We have install the package of Qiskit, and then there are certain tutorials that anyone can watch from YouTube and learn how to use Cosm simulator.
Please share these resources for working with this quantum simulator, please.
I'll share it personally.
Yeah,
after
please. Yeah, then I'll share it with the participants.
Okay.
Name, write
You can,
that name.
yeah. Can you write the
Chat box, please?
I've written the name of the simulator, Cosm simulator. It's
In
this
chat
is
box,
the name.
I cannot see.
Okay, sorry. It's now it's right?
Yeah, it's visible. It's visible.
So, any other query? If there is, I think that's it from my side actually. No.
Yeah, that's fine. You have really covered very deep details of the topic. Your digital simulation.
Okay.
We have
Thank you.
given, yeah. Thank you so much, Rohit, for giving the detailed insight into the topic that you have covered. And we are really enriched with your knowledge, like the way you have delivered the session. Thank you so much for being here.
Thank you, ma'am. It's my pleasure to be here.
Thank you. Thank you. Okay. And with this, we come to the end of this session for the day. Tomorrow we will have session at 10 a.m. So kindly join the session before time. Thank you so much.